Welcome, future docs. Let's dive right into today's explainer. We're kicking off our clinical rounds with an absolute physiological marvel, an anomaly, really. We're looking at an organ that completely defies what we usually assume about how the human body actually works. Think about this. How can a human heart just keep beating outside the body? It's the ultimate medical mystery, right? Picture it, a fully explanted heart sitting right there on a surgical tray, totally disconnected from the brain and the vascular network. And yet, it keeps pumping. I mean, it sounds like pure sci-fi, but this is a profound, everyday reality you are absolutely going to encounter in your clinical careers. So to crack this case today, we're going to look at 1. Biological hierarchy, 2. The autonomous engine, 3. The SA and AV nodes, 4. Transport and preservation, and finally 5 clinical interventions. Let's get to it. Starting off with Section 1, Biological hierarchy. Now, as anatomy students, you guys already know the drill. The human body scales up from simple microscopic structures to full-blown complex organisms. We've got our 5 levels here, starting way down at the cell, leveling up to tissues, then organs, systems, and finally, the whole organism. And the heart? Well, it acts as a highly specialized organ, doing the heavy lifting within a massive interconnected circulatory system that ultimately sustains the entire organism. But let's zoom back in for a second, right down to the microscopic level. You've got millions of specialized cells locking together to form tissues. In this case, the myocardium, that incredibly thick muscular middle layer of the heart. Now check this out. 99% of these are just your standard contractile muscle cells, linked up by intercalated discs to pump blood. But they don't act alone. There is a tiny, incredibly powerful 1% of cells in here that holds the absolute key to our beating heart mystery today. Which brings us to Section 2. The autonomous engine. Let's tackle that opening question head-on. We all naturally assume the brain runs the whole show, right? But take a look at this. The brain, via the autonomic nervous system, specifically using the vagus nerve and the sympathetic trunk, well, it merely influences the heart rate. It doesn't actually control the beat itself. Nope. The heart muscle has its own superpower, autorhythmicity. That means localized control. It can actually spark its own cardiac action potentials at a fixed rate, completely independent of the brain. Pretty wild, right? Moving on to Section 3, the SA and AV nodes. Okay, let's look at the physical wiring. Trace this electrical pathway with me. The signal originates up in the upper right atrium, right? Then it travels down to the atrioventricular septum and shoots straight along the bundle branches and out through the Purkinje fibers into the ventricles. What you are looking at is literally the anatomical wiring diagram of life. And the real star of the show here is the sinoatrial node, or the SA node. This little cluster of cells is the heart's built-in natural pacemaker. Here's exactly how it fires off, all on its own. When these resting cells are sitting at a negative charge, you get the slow, steady leak of sodium ions until, bam, it hits a threshold. Once that threshold is crossed, calcium ions flood the cell, causing a spontaneous depolarization that triggers the entire heart to contract. Boom! No brain signals required whatsoever. But hold on, we can't just have that massive electrical signal rushing everywhere all at once, right? Enter the AV node, or atrioventricular node. This little guy acts as a crucial electrical doorway. It actually catches that impulse and slows it down between the atria and the ventricles. And clinically, why do we care? Because this split-second delay gives the atria just enough time to efficiently squeeze blood down into the lower chambers before the ventricles contract. Basically, it keeps the whole system from short-circuiting. It's a brilliant bit of engineering. All right, Section 4, organ transport and preservation. Just look at that number, 4 hours. Because the heart comes equipped with its very own SA node and doesn't wait around for the central nervous system to tell it what to do, it can actually survive outside the human body for up to 4 astonishing hours, just chilling in an icebox. So how does this actually work in practice? Let's break down the biomechanics. Medical teams use extreme cold to artificially hit pause on those electrical impulses from the SA node. The beating stops, which drastically conserves the cellular energy in the myocardium. While it's in transit, they keep the organ fed with essential nutrients. But the absolute coolest part? Once you transplant that heart and warm it back up to body temperature, that autorhythmicity wakes right back up and it just resumes beating like normal. It is literally like restarting an engine. And that leads us to Section 5, natural versus artificial pacing. So let's contrast these two setups. On one hand, you've got a healthy, natural sinus rhythm, flawlessly dialed in by that SA node. But what happens when that node fails? Say a patient develops a dangerous bradycardia, an abnormally slow heartbeat. That is exactly when we step in with mechanical intervention. An artificial pacemaker, which is just a tiny battery-powered generator tucked under the skin with leads wired straight to the heart, literally takes over that electrical pacing to save the patient's life. Of course, pacemakers aren't our only tool. When the heart's natural wiring goes haywire, resulting in tachycardias or fibrillations, we've got an entire arsenal of modern solutions. We can prescribe antiarrhythmic meds to tweak those cellular electrolytes. If that doesn't work, we can go in with catheter ablation to intentionally heat or freeze irritable tissue. We can use cardioversion, a literal electric shock to stun the heart right back into a normal rhythm, or put in implantable defibrillators to automatically catch life-threatening rapid beats. As future docs, these are going to be your essential tools of the trade. All right, so we've covered a ton of ground today, zooming from the microscopic cells all the way up to the macroscopic organ. And stepping back to look at all this, it's so clear that the heart isn't just some basic biological pump. It's a completely autonomous engineering masterpiece. I mean, it beats 100,000 times a day, pumping 7,500 liters of blood, all without us having to form a single conscious thought. So, I'm going to leave you with this thought. Armed with this deep dive into the SA and AV nodes and the sheer marvel of autorhythmicity, how will you innovate alongside nature's greatest autonomous machine? What's going to be your contribution to the future of cardiovascular medicine and bioengineering? Keep that in the back of your mind as you continue your clinical rounds. Thanks so much for joining me for this explainer, and I'll catch you guys next time.
Like and subscribe.